We're going to pick up back in section 7.1 today with decimals, and I think that we had gotten to decimal square grid. Does that sound right to you guys? Yeah. Okay. So a decimal square grid is simply a 10 by 10 grid that contains 100 small squares. That is, it's going to have 10 columns and 10 rows. So I'm going to do my best to draw it accurately, and you do the same if you would. We're going to draw a big old square, and you're going to split the square into 10 rows and 10 columns. And yours will undoubtedly be better than mine because I'm already struggling. They should look approximately equal. And yes, I realize mine don't. So if I've counted right, there's 20, or there's 100 little squares there. And I'm supposed to shade in or draw in a number that represents the number 2300ths. Okay? So 2300ths would be shading in how many of these individual squares? 20 of them, and then 3 more. There's 20, and then there's my 3 more. All right. More or less, there's 23. This square represents a unit now, and then each of the individual boxes represents 1/100th of a unit, which is why we're shading in 23 of them. So this is a decimal square grid. You've probably seen them before. And they're great when you talk about using this idea to talk about adding decimals together, right? Because you can just shade them in, much like when you do with adding fractions, which you guys were thinking about some deals with fractions in the last chapter. All right. A theorem, a rational number, a over b in simplest form, can be written as a terminating decimal if and only if the prime factorization of the denominator contains only 2's and 5's. So this is actually telling us when we are able to change a fraction into a decimal that stops. So terminating decimal is a decimal that terminates, it stops. Okay, you've seen other kinds of decimals that don't do that. They're called what? Repeating is the one that you've seen probably most frequently. You've seen repeating decimals like the 0.3 where you put the bar on top. So this doesn't always happen, right? We don't always have the ability to write it in a stopping kind of format, a terminating format. There's also other numbers that don't have that repeating and they don't terminate. Can you think of one? Pi. And the issue with pi is that it's not rational at all. And so we're working with only rational numbers, so we're not going to encounter working with pi in this chapter. But that is another way that something cannot terminate, is that it has an irrational expansion, which would be something like pi. E as well, if you've seen E in numbers. Or you've also seen it when you've done things with radicals, like square root 2. It has that same problem. It's irrational, so it doesn't have any terminating form, nor does it repeat.
Doesn't pi eventually stop?
Nope, it doesn't. So every now and then you'll hear about some crazy person, and I'll call them crazy, who memorizes the first 1,000 digits of pi or something like that. I don't know why, but they do. That's just the first 1,000 of them. It will continue on past that. Yeah.
They must have a lot of time.
They must have a lot of time, I agree. I don't have that much time, so I'm not going to do that today. This tells us, however, when we are able, in fact, to do that is to write it as a terminating decimal. It tells us we're able to do that when we are able to factor the denominator, so prime factorization of the denominator, and that prime factorization contains only the numbers 2 and 5. It may contain only 2, or only 5, or lots of 2's, or lots of 5's, or some 2's and some 5's. It doesn't matter, but as long as it doesn't contain anything besides 2's and 5's, we're in good shape. Now there's one thing that this doesn't say right here that we have to make sure of. We have to make sure that the fraction we're looking at is in lowest form first. So if there's the ability to simplify the fraction to start with, and you guys know how to do that, we did that all in the last chapter, you need to start by simplifying the fraction, okay? So the first thing you have to do is to simplify the fraction. Now the examples that I've gotten on here, have put on here rather, 3 over 8 and 5 over 12, they're already simplified, right? So it's going to look like we're not doing that step, but it's because the two numbers we're dealing with don't have that step that needs to be done. Are you guys with me? Okay, good. For instance, if I started with the number 3 over 6 and you tried to factor the denominator, how does the 6 factor? 2 times 3. And if you strictly used this definition with this factorization, your answer would be no, it doesn't terminate because it has a 3 in there. That's a problem, though, because the 3 that's in that denominator, it actually reduces with what's in the numerator, right? So this fraction's actually the fraction 1/2. And you do know that 1/2 has a terminating decimal. What's it look like? 0.5. Okay, so don't be misled. You have to do that simplification first in order to have the details right at the end. All right, so what we're going to do, though, is we're going to take the denominator in these, after it is simplified, which these are, and we're going to take the number 8 and we're going to factor it. Now, factoring is something that's in the last chapter of the Elementary Math 1 class that we do. So I'm going to show you a couple of ways to do factoring for those of you who haven't taken that class yet. One of them is factor trees, which is the one that's most commonly taught in public schools and or in elementary and grade schools. So if you take the number 8, you say, what could 8 factor into? 2 and 4. And then you take the number 4 and you say, what could 4 factor into? 2 and 2. So you find out that 8 is, 2 times 2 times 2. Or you might, in fact, even write it as 2 to the 3. The point of all that, however, is the factorization only has 2's in it, right? Because it does not contain anything except for 2's and 5's. It doesn't contain 5's, but that's okay. Because it doesn't contain things like 3 or 7 or 11 or 13, any of that, this will terminate. Okay? That's what this definition says. The denominator contains only 2's and 5's. And if you want to change the word and to say and or, that's okay. 2's and or 5's. All right, so this one terminates. And the question asked after that then is that if it terminates, write it as a terminating decimal. Do you remember how to write things as terminating decimals from a fraction notation? And don't tell me I put it in my calculator. I know you can do that. Something else. Yeah, it's just division. You want to remember that that fraction bar just means divide. So if we're working on changing something into its decimal notation, we're going to take the numerator, which is 3, and divide it by the denominator. We may need to put the decimal point in zeros and things like that afterwards. And we would say 8 goes into 30 3 times. And then 3 times 8 is 24, which gives me a remainder of 6. Hang on, I'm moving some stuff over. All right, and then I'll bring my 0 down. 8 goes into 60 how many times? 7. 7 times 8 is 56. Subtract, what do I get? 4, and bring down another 0. 8 goes into 40 how many times? 5. 5 times 8 is 40, and I get to stop when I get to the 0 at the end. And if it's terminating, you will always eventually get to a 0 at the end. It may take several iterations of this, but you will always get to 1. And then the decimal point comes straight up from the decimal point in the dividend right here. So this decimal point goes straight up. So my expression is 375 thousandths. And if you wanted to confirm that, of course, you have calculators. There's nothing that's preventing you from being able to say, I'm going to put 3 over 8 in my calculator to see what happens. And sure enough, it will confirm for you that this is the decimal point and then 375. Okay, so far so good? All right, let's try this then for the numbers 5 over 12. So we're working on this one. Already in reduced form, right? 5 and 12 don't have any common factors. So we take the number 12, and we could do a factor tree, but I'm going to show you another option, especially 12 is not a big number. I get that. But let me just show you another way to deal with this if you did have something a little bit larger. Another way to do the division is to do the division. I make it go down the page. You can make it go up the page the same way here. Is to say what goes into 12, the smallest number. 2. 2 goes into 12 how many times? 6. Okay, so I've just got this division. This is division upside down. That's what it looks like. Okay, but then I do it again. 2 goes into 6 how many times? 3. Right, and 3 times 2, or 2 times 3. You could have switched it either way. I wrote it backwards, but all your numbers are right here. These are all the factors, 2, 3, and 6. So you're just looking for things that divide them with prime factors. So normally I would have written it like this. I don't know why I didn't that time, but there they are. So my factors of 12 are 2 times 2 times 3. Will this terminate? No, this is non-terminating. Why? Yes, because it has a factor of 3, in particular that 3 being in the denominator. If it had factor of 3 in the numerator, that I don't care about. It's only the denominator that we're factoring after the problem has been reduced. Any questions on that? Okay. Our next thing in this section, last thing almost, we're getting awfully close, is comparing or ordering decimals. So if we're trying to figure out which decimal is smaller or larger, or putting them in order from smallest to largest or largest to smallest, what we do is we line up the numbers by place value. And in particular, that means that we usually line up the decimal point to start with. And then we read the number from left to right to look for the first place where they're different. First location where the numbers are different, and we compare the different digits. So it is highly unhelpful, for me anyway, to look at this list the way that it is. Looking at it in a line like that is just the height of unhelpfulness. Okay, so we're going to write them vertically, one on top of the other, if you will. So I'm going to start with, I've got 13, then I've got my decimal point, 4919. Then I've got 13 in a decimal point, 492. And they really have to line up. I mean, like, you need to keep them neat and tidy, otherwise you're not going to be able to compare them any easier with this format. 13, decimal point, 49183. And then 13 with a decimal point, 49199. Okay, is there 4? 1, 2, 3. I think I got all 4 from there. 1, 2, 3, 4. Yeah. So we're just going to go line by line, or column by column, if you will, and recognize all the ones match. We're just going to go until they don't. All the 3s match, all the 4s match, and all the 9s match. So it's the third decimal place, the thousandth place before these differ. Agreed? So let's compare them. What do we see? Do we see one smaller than the other, one larger than the other? What do you see and notice in this first column where they're different? Yes, the second one right here is larger than the other 3 because it's got a 2 in it. 2 is bigger than 1. So this is my largest one. It actually says from least to greatest. So this is my greatest value. So if I'm sort of going to number them, and I will for the moment, this is number 4 in my list. It's the 4th one because it's the biggest. All right, so we have now eliminated this from consideration. I don't need to think about this one anymore. I've already identified it's the last on my list. I'm only looking at the other 3 now. So looking at the other 3, they all have 1s, in which case I need to go on to the next decimal place. So the next decimal place when I'm considering, I've got a 9 on the top, I've got an 8 on the third one, and I've got a 9 on the fourth one. So what can you tell me? 8's the smallest, right? And there's only one of them. So this one right here is my smallest. So it's going to be the first one I list when I'm listing them from least to greatest. So again, just like the last time, I ignore this problem now. I don't need that value at all because I've already decided where it goes in my list of numbers. And I'll look at the last 2. Now the last 2 both match on the 9, which means the first place they differ is the last decimal place that's listed. The one at the top doesn't have anything there. What does that mean? It's a 0. And if it helps you to write it in there to think about it, then do that. It's a 0. And the last one is a 9. So what does that tell you? Between those 2, which one's smaller? Let's say it that way. Right, the first one, the one on the top. Between those 2, that's the smallest, which means it's the second smallest. Very good. That's exactly what I was going to write down. second smallest, so we'll call it number 2. And that leaves this one here to be the second largest or the third number in my list. Now, this is the work that you're going to show to support your answer, but your answer is not this mess. Mine looks like a mess anyway. I don't know what yours looks like, but mine definitely looks like a mess. Your answer is actually writing them out from smallest to largest. So the smallest number that was listed was the 13.49183. You can put a comma if you want, or you can put the less than symbol if you like that. The second number listed was the one in the very beginning, 13.4919. The third number to list is the very last one, 13.49199. And then the last number to list was the second one, which is 13.492.
So do they have to be listed in horizontally?
You mean like listed in a list like this? No, they wouldn't have to be. You could reorganize them vertically. Sure, that'd be fine. Just as long as the one on the top is your least one and the one on the bottom hand is your last one is the greatest one. Yeah. Any other questions on this one? Okay, one more thing in this lesson. You've seen this word before. Where have you seen before the word tithe? Church, right? And so when we say the word tithe in church, what do you mean? Or what is 10%, right? So when we think about the word tithe, we think about the phrase or the decimal, the percentage 10%, which relates to a decimal point of 0.1. So the meaning of the word tithe, though, if you were to sort of look it up in the dictionary, actually means 1/10. Hang on. Part of something. Now, the way that we in the evangelical Christian community interpret that is 1/10 of the income you have coming in, right? So somebody pays you for babysitting or working at Arby's or your job on campus or whatever it is, you take the top 10% and you give it to God. That's how we interpret it. Actually, if you look real carefully in the Bible, the Pharisees and things interpreted it differently, and they gave 1/10 of all kinds of stuff. 1/10 of your spices is actually located in the Bible. I don't know about you, but I don't want to go and try and figure out 1/10 of my nutmeg. It just isn't helpful. But it's 1/10 of something. It doesn't have to be money, is my point, right? So some people will talk about this even now as 1/10 of your time, or something like that, when you're talking about what should you be doing as a part of your faith. And so the question is, how does that relate to decimals then? Well, 1/10 is understood to be 10%. We can also write it as a fraction, but it can also be written as a decimal. What's the decimal? Yeah, 0.1. 1/10, or like a dime out of a dollar, right? So this is how it. So let me just write that out then. This is the decimal, and we call it 0.1, right? And we talked last time about how that's not real good language, but that's how we say it in common language anyway, 0.1. This is actually read as 1/10. If you read it properly, right? This is 1/10. All right.